Good afternoon, everyone. Welcome to our tutorial on Neurosymbolic AI for grounding, instructability, and explainability. So, according to the Gartner curve recently, Neurosymbolic AI is used for trustworthiness and many things. But we have to improve it recently by adding like grounding, instructability, and explainability. So this curve talks about that the use of trustworthiness is increasing as of now, the time of June 2024. As you are sitting in this tutorial, so I would like you to all spread the word using these hashtags for explainability, grounding, and instructability. These hashtags will be important for our tutorial also. So please spread the word. And we would also like to share, this is one of our group's knowledge infused learning neurosymbolic AI for explainability, interpretability, and safety book coming up by Cambridge, which will be published in summer 2025. So today's talk will include all of these topics: neurosymbolic AI and instructable AI, vector symbolic architectures, grounding with retrieval augmented generation, explainability with knowledge infused learning, and open CHA, which is a language LLM based conversational agent for health. So I will hand over to Dr. Gaur, who will be talking about our first talk.
Okay, so let's get started with the core part of the tutorial. So the central question that we wanted to ask ourselves when we are looking at neurosymbolic AI for EGI, not the AGI specifically, is how do we go about reducing the black boxness in these large language models, right? So, okay, this is, okay. Okay. Anyways, this is not working. Okay, so there's a trade-off between what is a model size and how the explainability goes in these large language models. So we start with, we all know about the very simple models like Elmo and ULM-FIT and BERT-based and GPT-2, right? And essentially over the time when things progresses, the explainability components in these models has slowly depleted as we go as we extend the number of parameter sizes. Okay, so we know that in the very beginning of Elmo, that way of explainability was through attention maps and feature visualizations. And most of us already know about Line and SHAP as a very primitive initial methods for doing explainability. And then we go forward, we say that, okay, as we have ULM fit, we look into the layer analysis of these models. We look at the activation patterns of these models, how these neurons are getting activated as the new form of information is penetrating. And then we have even more better methods of explainability, looking at attention analysis and probing tasks. So probing tasks was pretty much an interesting work where they say that in order to do a topmost classification of a sentiment classification problem, then the model should be competitive for doing the part of speech tagging and verb phrase extraction kind of a simpler activities, because that's how you build up to the sentiment classification task. We go further. If you go to GPT-2 llama models, we say that okay, there is a sort of explainability designs for token attributions. We look at hidden states with sparse autoencoders, right? The recent work from Google DeepMind on the mechanistic interpretability on GPT-2 and Gemma models sort of falls into the bucket of areas where we talk about GPT-2 and Llama 1 models, right? When we look at GPT-3, the best we can do is do a behavioral testing, right? We try out with prompting methods and figure out that what behavior the models are able to show us. And some of the times the chain of thought of prompting works, and sometimes the chain of thought of prompting doesn't work, right? So going further, if you look at Palm and GPT-4 kind of models, the way of interpretability and explainability still remains a question, right? The max you can do is just to examine them with the information. And the reason we kind of question this is because we had an analysis over on a legal data set with some folks in the legal domain, and we found that the data set was 50-50. There are 50-50, there's a 50-50 chances that a prosecutor will win the case versus a defender will win the case, right? And it's the same behavior what we saw in Claude Sonnet. We saw the same behavior in GPT-4 because the data set was 50-50, right? So sort of this behavior falls onto the question that explainability in these models is still a question for further investigation. So if you boil down this entire process of hierarchies of these models, essentially what we are trying to look into is that we have the data, we stitches to these models, we get a particular decisions, right? But most of these decisions are sort of the ones where we cannot make sense of what these decisions mean in real life or in real domains. So that's where we step into the design, where we look into something that is more tangible, something that we understand, right? Something that we can represent, right? And that's what we consider as the symbolic piece of the knowledge, right? And we want to see that can we transition our models that we see on the left-hand side into the models that we are looking at the right-hand side, right? Where we want to see that can I have a way of looking at the deep neural networks in a form that the information is sort of is a kind of, let's say, complementing each other as opposed to simply driving the decisions based on the data-driven behaviors, right? So in a high level sense, if you want to see this, it's going to be like I have a knowledge graph embedding model, right? Developed by, let's say, if I take trans E or trans D as the knowledge graph embedding strategies, and I know that for every concept in my input domain, there is a corresponding representation of that concept, right? So what we are doing is that we are trying to look into how these embedding spaces in the knowledge space can be utilized in understanding the embedding spaces in the neural network side, right? So this is how we are looking at these two points together. So on the left-hand side is sort of an embedding that you see from the data, and on the right-hand side is an embedding from the knowledge graph side, right? Okay. So in the bottom line, what we really want to achieve is this three phenomena with the neurosymbolic AI, and that's going to be the crux of the tutorial for today in today at AAAI. Right. So first of all, the first thing that we really want to go for is an instructability component, and then we gradually goes to the grounding and then explainability. Right. So the instructability part is pretty interesting. We want to be very cautious saying that it's not instruction tuning. It is sort of an instructability in terms of and sectioning, like looking into where in the model do we really need to put down the instructions and how the models adhere to those instructions, right? So there's a very interesting task by Princeton University on skill acquisition, right? So what they're trying to do is that they have the data set, they want to try, and it's a nice data set called the skills. And it says that if I have a particular skill that I want to teach to the LLM, and I can give a particular example, it shows that the skills sort of it can understand those skills very well. But the question is that, can I use that learned skills in downstream applications, right? So those are two different things as a property, right? And the second part is a knowledge gap management that we will talk about, where we want to say that, can I quantify the knowledge gap? Can the GPT tell me when it knows things, and can it tell me when it doesn't know the things, right? Rather than creating some information that I cannot verify or validate, can I do some kind of a knowledge gap management or measurements, kind of like a kind of an activity? So that's the second part of over here, right? And the grounding part we want to look into is most about the symbolic grounding and the functional grounding, where we say that, can I ground this information using a knowledge graph and a knowledge base? A very simple example to do that was used in back in the old time in machine learning was a k-nearest neighbors, right? I know that, okay, does this sort of information has a nearest simple samples. I can bring those information samples together and I can give it to a model and can understand those patterns very well. An elevated version of k-nearest neighbors is a RAG, right? A retrieval augmented generation, where I have a vectorized database and I want to examine those vectorized databases and how those can be used into the LLM space. So we'll go about those as we go forward in the grounding side. So in the explainability side, we really want to look into the design of what explanations means in terms of user understandable explanations as opposed to explanations that we talk about in terms of the attention map or attention scenario. So we want to translate those attention scores, those attention matrix into something that is more more understandable and interpretable by the individuals. So this boils down to one of the concrete definition that we want to start with, which is the neurosymbolic AI is not just about logic, it's not just about constraints, but it's also about incorporating a broader form of knowledge. We look at lexical knowledge, which is sort of a dictionary, right? We have a concept and a bunch of words that are similar to each other. And going from there to look at the common sense and constraint-based knowledge informations that can be translated into some sort of a machine readable form and be injected into the LLMs or injected into the models for downstream tasks. Okay. So how does this neurosymbolic AI design falls into the large language model space or in the era of large language model space, right? So we'll talk about some of the applications where we think these things happens, and we'll stitch through these applications as we go forward. So first, always is definitely one of the exciting applications is called the Copilot, where right now there was a recent work from Nuance on called the DAX Copilot, which is able to integrate or actually essentially understand the conversations between a patient and a clinician, right? And understand that what that conversation means, right? But that method has some kind of a pitfalls. And the pitfall was just that the clinician has to start with some jargons. The clinician has to start with some sort of a clinical level descriptions so that the LLM understand what those concepts are. And then the clinician has to go for another round to figure out what those jargons means in a simple language so that LLM can understand both of them, understand the mapping, and then compute a summary, right? So that was a pretty interesting example of looking at the Copilot design in the healthcare space. The second is there was a recent work on the implicit personalization with neurosymbolic AI design, which essentially discusses how these personalization approaches or methods in LLMs can be made into more implicit as opposed to be explicitly personalizing these content, right? And subsequently, we have works on the workflows. There's a set of work on the attributable reasoning, which we will cover eventually. And there's another set of interesting work that was really discussed in AAAI, which was about debiasing these models using US labor data sets. So there was a lot of like it was interesting insight that was talking about that LLMs have considered what do you call that Instagram influencer to be the highest paying job in United States of America, right? Which was not true because according to US labor, it's a completely different professions. But it was interesting to figure out that that was a peaked point in the GPT and the GPT-4 spaces. Okay. So where does this all started, right? Where does this all integration of LLMs and neurosymbolic AI started this process? So this is a very interesting paper which was released as language models for language analysis of models, which was the first model called Llama. It's not double L, it's a single L. It's just Llama, right? And it actually talks about a very interesting case where it says that you have the knowledge graph at the top where I have the information about a person, Dante, born in Florence. And my query is that subject predicate, and I want to predict the object, right? And that's the answer that we really want to do it, right? So this is simply a link prediction problem or a node classification problem in a specific knowledge graph space. Now, what they did was they turned this into a mass modeling strategy in the bottom hand, where they say that Dante was born in the mask, right? So the model will try to predict what going to be that mask is, and that's how they learned a better embeddings for Elmo, and they analyzed Elmo and Bert, and that was the first set of strategy to start with the Llama sequence of models, right? So this was a pretty interesting example of translating the entire knowledge graph space into an embedding of the vectorized representations. So this essentially talks into that how this neural AI and symbolic AI are connected, are overlapping. They have been considered as dissociated set of activities, but they sort of overlap with each other, right? So when we have neural AI, we all talk about data, we talk about hyperparameters, we know about activation functions, we talk about the computing power, the loss functions and optimization functions, but all of these factors, all of these properties do exist for the symbolic AI piece as well, right? So we talk about activation functions in symbolic AI. We talk about symbolic activation functions, sorry, the loss functions and optimization functions in knowledge graphs, which is being used to construct the knowledge graph embedding strategies or embedding methods. And then gradually we can even think that symbolic AI has this constraints and workflows in the bottom left, right, where or bottom right, which essentially can be borrowed into the neural AI aspect as well. Okay. So let's just start and a simple example of how this two overlapping structure that I just talked about translate into the real world, right? So let's just take a simple benchmarking example of how these information play around in the LLM spaces. Okay, so this is a very interesting example about a recent event activity that happens in Mayo Clinic, where organizations across United States wants to analyze that what is the wellness dimensions of employees within that organization. So they have 8 classes, very crisp, very clear 8 classes in the designed by the domain experts, which is about social, emotional, spiritual, intellectual, physical, environmental, financial, and so on and so forth, right? So the task is that you want to utilize this wellness dimension strategy to examine that what is the wellness of a particular employee within an organization, right? So what they did was they started a simple data set process where they constructed these data sets across 4,000 users, right? So they have information about those 4,000 users. They fill up a very big form about the wellness dimensions, and they being assessed on whether they are having a physical weakness, emotional weakness, intellectual weakness, and so on and so forth, right? So the objective was, can I turn this into a learning model where I can get those information from the user and able to classify this information across these 6 buckets, right? So that's what the simple case is. Now, interestingly, what do we have? We have is that across these labels of these wellness dimensions, we have definitions associated with it. That's the only sort of a domain knowledge that I know of that's available to me in order to teach the neural network across for all of these classification tasks. Okay, so we started with a simple design, and I would just be a high level on this design side and sort of give you the gist about what exactly happening in these designs. So first design is about attention map, which I started with in the beginning of the tutorial, right? That I have an LLM, I can extract attention matrices, I can visualize that attention matrices through attention maps, right? Now what I'm trying to do is that for every attention matrix that I have from my model, I have a mapping between its words and the concepts, or words to the words. It's kind of like a self-attention matrix. I'm talking about words to words mapping, and that's a square matrix that I'm referring to, right? So that matrix that I'm looking at, I'm trying to understand which word did model pay attention to when it was doing that classification, right? That's a design one. Now, once I have extracted those set of words that the model is looking at, I have a bunch of sequence of words that I consider as important and some set of the words that are not so important at all, right? Now I want to see that whether those words are present in the explanations that are being given to those users by the experts. So I'm looking at 2 things. I'm looking at the classification that my model is giving. And the second thing, I'm looking at whether the model is looking at the right set of entities within those forms that the employees have filled in, right? And the corresponding explanations that the experts are giving, right? There are 2 things. So experts have given explanations on whether they consider that a particular employee as emotionally weak, spiritually weak, intellectually weak, and so on and so forth. And they have a classification for that employee, right? So I want to see both of those behavior inside. I just don't want to rely on the prediction, but I also want to look at the explanation part as well, right? So the second aspect of this picture was where we want to look at the same tuning of LLMs, but now with that in context learning with definitions, right? So I want to construct a prompt where I would be giving this LLM a particular sequence of inputs in the form of a prompt, where I will give the model a set of definitions for every particular input. So consider this a prompt of this following kind, that you have the input query, and then you have a bunch of rules, and those rules are nothing but the 8 definitions that I'm referring to, right? And for all those definitions, I'm just asking that, giving it to the LLMs and figuring out that what type of classification it gives and what set of explanation it provides me, right? In that process, you can still fetch out the attention matrix of those models and try to understand what those attention matrices translate to in terms of the natural language text, right? Which is again nothing but a bunch of words, and you want to map that bunch of words to the explanations, right? So that's the second sort of a design to understand whether the entities or the attentions are being mapped, or the right set of words are being mapped or not, or the model's attention is focused or not. Okay. The third design is sort of not giving all the definitions at once, but rather giving the definitions in some sort of sequence. Assuming that I tell the model that here's a query, give me a particular prediction and an explanation, then the model gives it a wrong answer, and then I give it another hint, right? I give it a hint to the first definition, I give it a hint to the second definition, so on and so forth. Now, why am I doing this particular process? I'm doing this particular process to figure out whether the definition that I give it all at once gave some information to the LLM, sort of patterns between those definitions, or is actually understanding those definitions line by line. And that's how it is using them in the downstream classification or explanation generation task. So if you give LLM all together, all the information, it has a different behavior compared to giving them in a sequence, right? So let's say if I give the person, if I say the physical illness is the first definition, in the second definition I say spiritual illness, then even if it's not present, there is sort of a new pattern that model will emerge, and maybe give it some sort of a probability values, not the high probability value, but a decent number that still exists in that particular experiment. So we want to see that chain of thought design in the sort of design 3 experiments. And the fourth design essentially talks about when we're looking at the questionnaires that the employees have filled as the exact template into their prompt. So I'm not in this process, the template got changed. We have the query, the 8 definitions, and now I have a series of questions that were asked by each and every individual for that particular scenario, right? So what we found in this 4 designs, right, there's some sort of discrepancies between domain-specific LLMs and general-purpose LLMs. So when I'm talking about domain-specific, I'm only looking at the ones that have been defined for psychology-related tasks like Scikit-BERT, Medalpaca, and those models. And then I am talking about general purpose, which is looking at Llama, Mistral, Phi, and those scenarios as the design, right? So first thing that we looked at was design for, when we look at this design 1, design 2, design 3, and design 4, we want to analyze this robustness of these models. So now this is where we want to focus on. The robustness have been in discussion in machine learning for so many decades, right? So we found that it is important that we look at the SVD design or singular value decomposition of the attention matrix as a way of robustness. So the criteria that we analyzed was that if the attention is way, if the rank of this matrix is extremely high, then the possibility is that the model is sort of like dissociated across all the input data. But if the attention or the rank of this matrix is relatively low, then I say that this is a more focused representation or a focused behavior of the model design. Right. So we look at these designs, and the answer is that the better model is the one which has the lower rank compared to a model which has the higher rank. Right. So we move it further with an attention overlap, that whether that attention that the model was looking at, and I want to check that attention to the ground truth explanations to figure out that whether that mapping happening or not. So the objective is that these 2 plots have to be an inverse rule, right? That's the simple design that we want to put forward. Now, this was on the domain-specific side, but when we look at the general purpose design of the model, now we found that in this general purpose design, we have a better representation. I think, yeah, it was relatively a better representation of the design compared to a domain-specific model. Now, this was very interesting and something very amusing to us, that the domain-specific models were not so significant in the performance compared to the general purpose models in this particular task, right? And likewise, when we look at the attention overlap of this model, we can see that the process of domain specific were relatively, I think, better in terms of the attention, but the performance was not so significant in terms of the design for. So this boils down to two architectures that we really picked off to be a good design strategy in this experiment. One was where we look at the questionnaire or the workflows based behavior of training the models. And the second one was looking at the in-context learning or the definitions. Now, extending this further, we want to see that how this workflow design essentially translate to in the further processes, right? How does this workflow structures go forward? Right? So that's where we step into a design where we look at the process knowledge infused learning, which is a framework of looking at how these workflows, these protocols, and these structures of questionnaires we translate into real activities in the LLM spaces. Right? So process is pretty straightforward. We have the domain data, we have the processes, which is nothing but in this case is questionnaires, right? And we want to translate those questionnaires into some sort of a mechanism of integrating inside the LLM spaces, right? Okay. So let's just translate this into a simple example that suppose there is a particular a post and the subsequent label is suicidal ideations, right? So we are talking about the mental health scenario and we have a particular post and we want to do this particular classification strategy approach. So what we are doing in the process knowledge infusion is rather than just giving up this input data and turning into a classification task, we are translating this into a particular series of questions. Now, for every set of input, we have a series of set of questions, right? And what we really want to do that for every input, the model has to give me an answer for yes, yes or no for each and every questions. And eventually on those probability values, I will be basing out my final decision. Right? So rather than giving the straight away classification, I'm trying to look at the questions in specific, right? And how does this questions translates to? The questions essentially translate to a particular flow chart, right? So what we do in this process is the question one, if it is answered yes, then I'm going for the question number two. If the question number two is answered yes, then I'm asking a series of set of questions. And if those are answered all, then I will be having a particular sixth question. If not, then I have a label in each of the cases. So I have a kind of a flow chart or kind of a tree where I'm trying to teach my LLM that whatever you're generating, generate like a tree, right? That means that whether you are answering this question, whether it's answer to this question is yes or no, and then subsequently going forward as processing sentence by sentences, right? So how does this essentially turns into? It's essentially that what we did was we turned this entire set of questionnaires that are already available into some sort of a flow chart and understanding what these questions are referring to and how they are translating into a particular flow chart, right? So we are doing the same process of wellness dimensions, right? Give into the mental health space. We have a questionnaire. We know how these questions are being structured. We're just creating a flow chart and we are trying to teach the LLM to follow this particular flow chart in making the predictions. So given a query, the model needs to follow a particular flow chart and then follows for a particular, like get you the final outcomes, right? So essentially what happens is that when you give an input data, the model looks at each and every sentences, right? And every sentence it is checking whether it's able to answer these 9 questions or these 5 questions, 6 questions, whatever it is, right? If it are able to answer that question, then it looks at the decision whether I'm able to move to the next set of questions or still I have to look into those questions again, right? So this process is sort of intractable and is also interpretable in the functionality, right? Okay. So how does this formulate into? This formulate into a very simple strategy of replacing the softmax design of your LLM spaces into sort of a decision tree design, right? So what you're stitching is that you're stitching a sort of a decision tree at the outcome, right? Where it is checking that whether for every sentence it is understanding, is it able to answer those questions or not? If the question is answerable, it has one probability. If it is not answerable, if it has those high probabilities. So it's just like twofold directions in all the cases, just like you see a tree on the left-hand side, right? Okay. So how does this translate into the direction of the model's attention? Is that if I have the same input which I was referring to, what am I doing is that I'm trying to look at those questions and I'm saying that, okay, based on those answers of yeses, I'm making the final prediction or the final label of that particular post. And what we found that by doing this behavior, just stitching this decision tree and this pattern of process knowledge across all of these models, you see significant improvement in terms of these models' behaviors, right? Which is like, say, these standard behaviors or like standard performance are relatively low, but that's what we found in all of these models. Considering the recent mental llama and the process knowledge that we tried out, even T5 was supposed to be a best model compared to a relatively larger middle bucket GPT-2 designs. Okay. Another experimentation that we performed on this design was on the agreement and the explainability score, that sort of like people agree more on the side of GPT-2's explanations and our process knowledge representation compared to GPT, considering to the middle bucket and mental llama. So this was very interesting insight from this work, because GPT-2 seems to be more interpretable in behavior compared to other gigantic LLM models. So you can, if you want to look at the interpretability part, then GPT-2 seems to be a good usage of looking at the mechanistic interpretability of how these models' attention matrices changes over the time. So sort of we found that in this behavior, the agreement with GPT-2 and process knowledge design was relatively better compared to all other models. Now, then we translate this into another segment of work where we explored this part in the social media spaces. Why we did it? Because whatever we were doing in the previous spaces were very much guarded with the right set of information. In wellness dimensions, I have the right set of their definitions. In terms of the suicidality, I have the questionnaires to help us with the right set of information and the process knowledge. But here we dive into a segment or a set of data set where I don't have those set of definitions. I don't have those set of liberty of precise and good quality knowledge as I'm seeing in the previous informations. The reason is, and to do this strategy, what we found of looking into the neurosymbolic AI piece was sort of step back into the design of topic modeling and word embedding spaces. And why are we doing that? Because those are the initial models of looking at how these words are being described, are being shared in the sort of input data, right? So we look into the symbolic spaces of these design into the picture of LTA and word to vec, and looking at the key phrases, and then looking at the hashtags. Now, one thing very interesting that we found in the social media spaces was the neologisms. What are those? And they are the really good hurdles for large language models as we see them. These are the set of words or the concept that people create to propagate their thought, but those words don't have any literal meaning in the vocabulary, right? So those words don't exist in the real world as they don't have any manifestation. Neither those words have any representations in the real world. So what we did was we sort of created for the symbolic piece, we sort of created a design of a lexicon in this figure, where we say that how these social media informations can be dissociated, can be understood better with LDA and with word to vec, and also constructing a lexicon of those words and how those can be represented into the embedding spaces. So we'll move forward and we'll see how these things translate into the neural spaces. So what we did was, when we have these lexicons we created, I want to do two sides of information. I want to look at the mapping of these semantic entities or semantic concepts into the concepts which are there into the labels. Either it's depression, addiction, anxiety, or whatever mental health label that I'm referring to. I want to find the mapping between these words and those concepts, right? And the semantic proximity is nothing but how am I looking at those similarities? Is this cosine similarity, or I'm looking at the Jaccard similarity, or which distance am I using to find that mapping of those set of informations? Now, after we have completed the semantic mapping and the semantic proximity, we looked at the index scoring of this design. The index scoring means that I want to see that within a particular set of words, how often they are representing these mental health conditions, and how much time this set of words are not representing those set of mental health related conditions. So after we have done this kind of a mapping of those scoring, I want to translate those information into the classification or to the classifier task. So what is this process? This process is not a standard process that we follow in machine learning or in deep learning strategy. That there's two reasons for it. One is that the model will be looking into those words which it has no representation of. If it hits those set of words, it won't be able to figure out what those words means. So sort of the decisions will be sacrificed. The second thing is that how those words translate into depression, mental health, or anxiety, or suicidality, or addictions, model has no idea about those informations, right? So those mapping is not existing inside these models by default, right? So the only possibility if you do it other than the structure is to have the loads of data and you put those corpus inside the model, right? So rather than doing that, what we looked into is that we looked into a way of constructing a lexicon and try to construct a mapping or a weight matrix, right? So this weight matrix that you see over here is what essentially we are trying to utilize to do the classification task of these models. So what am I doing is that I have the same set of words going into my classifier, but rather than letting the model find those weights for those words, I am giving those weights as an initial seed, right? So that those weights are being used to do the final classification rather than model starting it from the cold start, right? Okay. So how does this translate into the picture is that you are constructing this lexicon space over here where you are looking at anxiety and how those words are, and what is depression, what are those words, addiction, what are those words, and all of these words that you see over here are extracted from the downstream data sets of this in the social media spaces. So what we found in this inside of an experiment was pretty interesting is that if I look at this leftmost table, which is simply a machine learning model, right? Looking at the random forest as a simple model, we found multitudes of grains in that behavior by just incorporating those weight matrices. But what we also found was that this strategy seems to work much better than Mental Llama, Phi, and Mistral, which were used in the same process of doing the classification on the Twitter data, right? So this information tells me that if I have a predefined weights, if I have sort of a weights that I create manually by maybe using an autoencoder or variation autoencoders, and I learn that particular weight matrix, I can use that weight matrix as a seed to train my model in a way I want in a particular domain, right? So what we did was we took a model, right? And which in this case, we just took a llama for the neurosymbolic piece. And what we did was we just tuned the weights of this model by using the weight matrix learned from off the shelf by using the mapping, right? So mapping is what we did, and we looked at the weight matrix to do the final classification tasks, right? So this essentially goes into the final structure that where we looking at that there are some intrinsic challenges that still exist, which we haven't explored in the previous work, but they do exist in the LLM spaces. So the first one is definitely the consistency was an issue. The previous experiment that we found raised a concern about consistency of these models. We looked at the issues in terms of reliability because most of this information still don't exist and the predictions were sort of absurd in the performances. Another aspect was that the explainability, what we tested, didn't match to the expert level explainability, but still was some sort of a mechanism where we can map the generated explanations to the ground truth explanations. And the last part is like the safety aspect over here, where we say that these models are unsafe in the context of mental health scenarios because most of this information can be fabricated in the real world when we have the real world interactions. So this challenges sort of exist in the neurosymbolic designs that we explored in the wellness dimensions in the mental health space. And now let's just let's just take a deep dive into what these components represents in neurosymbolic spaces. So the first thing that we want to look into is a consistency aspect of this behavior. And to us, consistency was a challenge because when we looked at these models' attention matrices using singular value decomposition, we found a lot of uncommonality in the performances. Right. So, but we found that the model were not consistent in the behavior, and there was some sort of a attention and explanation gap. The attention the model is giving to those words were not there in the explanations, right? So we sort of looked, kind of examined that how we can look or penetrate into these model behavior. So a very simple example that we started with, that there is some inconsistency behavior inside the model, was just to paraphrase the questions or the queries that we were giving to the models, right? So when we were paraphrasing this information, what we found that the model just giving an information right now does not give information in like few seconds after that query, right? So another aspect of issue over here was that when we were trying out with the legal spaces, we still see the same sort of a problem. Because our data set was 50-50, right? We had the same situation that the model was giving us, okay, the winner will be the defender. After a few seconds, the prosecutor becomes a winner, right? So those sort of a discrepancy raised concern on the consistency aspect of the model. So what we sort of did was we did an empirical study just to focus on the consistency part of this model. So what we did was we took those queries that we tested on, we did a paraphrases of all of those informations, right? And we stitched those paraphrases inside the model. Now what we did was for all those paraphrases, the model gave me a set of series of responses. Now what I want to learn from the model is that if I give you 200 queries, let's say, right? What are the set of rules did you learn from those 200 queries? I don't really care about what your responses are or what your predictions are. What I really care about what are the set of the rules that you have learned from those set of samples, right? And that's what we want to emphasize on in the consistency part, right? So another example that we saw in the mental health scenario was that if I ask a model that if is seeking therapy is a sign of weakness, then the model says, no, it is not a sign of weakness. But after a few seconds, if I ask the same thing again, it says, yes, it is a sign of weaknesses in seeking the therapy. So now this behavior is not just in mental health, but we found that it's even do exist in the disaster management as well, right? So if I look at the crisis response as one of the challenging scenario where LLMs can be used, you do see the inconsistency behavior inside these model spaces. And these queries are very simple. If I elaborate these queries by population, by age, by location, and by weather and climate for every different state in the US, this becomes a very big set of a query to essentially look into the model's behavior, right? So that's why we looked at that there's a need for looking at the rules that the model has learned, right? So what we did in this strategy was to construct a design for training this model, what we call it as a SAGE. And the behavior of this framework was that given a series of input, which is the query or a sentence, the paraphrasing of all of those queries are being done. Then it goes to the target LLM. Target LLM gives the responses. And I am asking through prompting, what are the ROTs that the model has generated? I do this across 200,000 series of queries. And how am I doing that 200,000? Because I started with 2,000 queries and did a paraphrasing for each of them. And I escalated the size of my data set, right? And once I give the structure and I'm training the model in a particular design, I'm not training the model through a softmax, but I want the model to look at this graph, which is constructed through ROTs. So the graph that you see over here, right, in this structure is essentially the graph coming from the ROTs over here, right? The idea over the graph is that if certain rules are very closely related to each other, that means there's a consensus that the model is coming to. If the rules are very, very far off from each other, that means the rules are isolated, right? They're not so significant, not so informative, or maybe there are some edge cases that are coming into my input, right? So the idea was that to construct this graph and then you optimize this network over this graph. So essentially I want to do is that I want to do a cut over this graph to figure out which are my connected communities and which are not my connected communities. So I'm trying to construct that, okay, in this particular graph, over the period of time, are they constructing this as a closed communities, this set of as a closed communities, this as a community, and so on and so forth. So essentially is that if I'm not able to if I'm able to get a denser graph with less isolated nodes, that means I have a better score in my model compared to a graph where I have fragmented. So essentially consider this fact that if I consider a graph which is into a different set of communities, right, very dissociated, then I would have a very low score in the models, in the consistency. But if the score has to increase, that means I have to have a dense connected graph being formed on my set of rules, right? So that was the process of doing this sort of experiment of constructing a sage as one behavior. So how does this sage was designed? The sage was designed in a pretty simple strategy where we know of that given a particular sentence of an input, the model has learned a set of actions or action attributes from that input. And based on those action attributes, it is able to make an answer. Now, what is this action attribute? It is nothing but an attention matrix, right? It's sort of a attention that the model is emphasizing on, given a particular sentence and looking at the final output. So what we did was we sort of added ROT or the rule of thumbs on this particular design. So essentially what we are trying to do over here is that we are looking at the same set of rules, the sentences, and now I have a set of attribute for those rules as an input on which I'm conditioning my final generation. Now, what's the benefit of doing this is essentially that if I have a set of rules or rule of thumbs, then the model will just follow those rule of thumbs because it has seen those rules during the training, right? So I want to design those set of rules that I can construct to do the final predictions. Now this can go one step further so we do have improvements in this design with the Llama as a focus because it's an open source design of the model. But what we found was that this can even go further with a knowledge graph ROTs as well. So what is a knowledge graph ROTs and how can I construct those? That was the question for us. So what we did was we have the base LLM, which is the normal way of generating. Now what we are doing is that we are constructing a knowledge graph embedding for every set of my knowledge graph. So this representation of knowledge graph embeddings is nothing but a set of triples. It is subject, predicate, and object. That is what I'm considering as a rule, right? Now what I'm doing is that I'm conditioning my generation or my input over my input X by using the knowledge graph or the knowledge graph representation, which is HK of R, which is nothing but sort of representing the dense representation of the triples being concatenated with X to form and to be passed into the base LLM. So this design sort of gave me an idea that I can construct my rules using the triples and give it to as an input to the model's behavior. Now, this design seems to be a better design than training my model on a bunch of like 200,000 big of paraphrases and generating in ROTs from them, right? So rather than doing that, what I'm doing is that I'm having a knowledge graph of a particular domain. I'm extracting the triples from that information. I have a way of representing those triples as representation, and I give those representations as a concatenated vector to my network. Now, what's the benefit of doing that? I don't need to do a paraphrasing, and I can actually integrate my knowledge sources in a much interpretable and tangible manner compared to the rule of thumbs. Okay. So this approach seems to have a better design across some of the models that we tried out, given our limitations in terms of the computation environment. But we tried out tested with a mental health data set, which is the IMHI, the largest data set in the mental health spaces, right? And we try to see that this approach of SAGE by utilizing the knowledge graph embeddings as ROTs seems to be a better job across GPT-2, Mental Llama, and even the T5 models behavior. Okay. Okay. So this sort of puts a space for the consistency part. That in the consistency design, we can, so in the consistency part, we can say that the models was consistent with these the strategies of Sage variants, where we are trying to integrate the rules inside the model networks through ROTs and through knowledge graph triples. But we also can attain a sort of a better design to it by using an end-to-end strategy of rule of thumb. So I haven't tried out with the data set of ROTs, but what we did was we just looked at ROTs as a generated component from the LLMs, right? So through the prompting strategy, and we looked at that through the knowledge graph triples, you can include those triples inside the model network as well.
Spring technically starts like March 20th, 21st. Okay. It's like the spring the solstice, but that doesn't mean it's gonna be warm. Yeah. We'll know when usually April when the ground ground thaws is when we're sure, but I've seen winter return at the end of March. Okay.
Okay. So there is another segment of neurosymbolic AI that we are investigating, or we investigated, which was in the context of reliability. It was in the neurosymbolic spaces. There are 4 components of reliability. We look at the grounding part, which we will be discussing more detail in the subsequent segment of the tutorial, right? Where we looked at the grounding as in the form of an attribution, asking the LLMs to give me the citations for the sentences, right? And the second design was sort of giving more detailed version of this, where we are looking at how we can ask the LLM to give me a draft analytical report or draft report. I push it to the LLM and I can find the references for those sentences. Now, what aspect of this utility is going on is that when we are looking at when we are attending a conferences or a scenarios, we have the situation where we are taking notes as a presenter is speaking, right? And you want to go back home and you want to figure out what papers or what references those sentences refer to, right? So we can't do a Google search because Google search and scholars are not so efficient on these processes. So what we thought about is that how about we push those information inside an LLM and is able to attribute those citations. That was one of the experiment that we constructed on the grounding aspect of neurosymbolic AI. So the grounding essentially turns into the aspect of explainability as one of the aspect, knowledge gap resolution as another aspect, and the third component that we look into is the source attribution, right? So we'll gradually go into the deep of these aspects as we are moving forward this. So one thing that we found that when we were experimenting with knowledge gap resolution, we found that knowledge gap is also connected to the instructability aspect of the LLMs, right? So if I know that what the model knows about and what the model isn't aware of, I can use that as some sort of information to be integrated into the LLM, sort of understanding what those instructions are and how can we use them. So the grounding in neurosymbolic space has a little twist in the definitions, right? So we want the grounding is to be not just be situational assessment of what the domain I'm referring to, what is my task, am I doing classification or recommendation, but also I really want to look into this knowledge gap resolution as one of the important component of the grounding, right? So if I want to give the LLM a particular input and I get my classification, this just tells me that the model is capable of doing something, but doesn't tell me whether the model has a knowledge of using it in the downstream task, right? So if I tell the model, do you have a skill of doing an art, and it can generate an art and you're not satisfied with it, that tells you that, okay, the model did understand my query, but it didn't understand the semantics inside what exists in my query, right? So that's one of the things that we want to emphasize in the context of the knowledge gap. So there's a fantastic taxonomy about how these knowledge gaps are being represented across various applications in the AI spaces, right? So there's a sort of a language gap, then there's sort of a reasoning gap as well, and the explanatory gap in this in the language in the large language model spaces. So let's just look into this one part of the language gap, or what those language gap essentially means, which is nothing but paying attention to the important domain concepts. So as I said, into the part of the knowledge gap, as I said in the previous slides, that there is a way to investigate the attentions inside the model. We want to see that how do we do it in a much more better manner compared to what we were doing in some like looking at the attention, matching it to the final outcome and then seeing that whether those attentions are matching to the explanations or not. So what we saw that in this experiment was that there is a nice way in which this sort of information can be integrated into the LLM spaces, and the attention can be directed into the direction where I really wanted to be emphasizing on. So there was a really interesting finding that we found that if I have again a set of questionnaire, which I was just looking at in the prompting style in the wellness dimensions and in the mental health space, I can turn that into a really nice components inside my neural network or the large language models. So what you see over here is that there's a clinical T5 model which is able to highlight mostly all of the things as important in final classification, whereas having a particular questionnaire in mind, you can have a more targeted highlightings or the attentions inside the model with the right set of concepts which those are referring to. So what we are trying to do is that how we can achieve from going this side to this particular design of attention. And this is where I delegate this part to a subsequent tutorial, which will go in deep about this behavior of how we go from this segment of dense attention into more targeted attention mechanisms using a series of questionnaires. Okay, so there is another aspect of neurosymbolic AI that we looked at is called the instructability, which we started with, and we say that the instructability is definitely not instructability in terms of instruction tuning, but it is much more than that. And why we think that is because there is a simple illustration which was released by a recent paper, I think it was in 2024, which tells that instruct LLMs, base LLMs, and chat LLMs are no different. They are essentially the same. Right? And it says that the difference between these models is just adding new tokens inside the model's text. So this information over here is sort of tells you that only 7.8% of the information or the knowledge is contributed by instruction tuning, whereas 77.7% or roughly 78% is sort of the information that the model still have is the old version that came from the pre-trained behavior. So that was a very interesting factor for us to investigate. And we sort of investigated this further with the Mistral. So this was on the left, it was the Llama. When we looked at the Mistral, we only found that 5.2% was essentially being identified as a new token that the model has learned after a week long of instruction tuning, right? So instruction tuning on the Llama, on the Mistral, only contributed 5.2% new tokens, whereas the around 83% remain the same as it was in the base LLM. So the question here is that how is different the instruct model from the base model that we are using, right? Okay, so with this, we looked into the fact that when we are doing the instruction tuning by the instruction data set, the token level impact is very, very small, right? So we don't have the instruction tuning does not make any new changes to the behavior. The behavior is still the same, right? And maybe like your query is sometimes sort of a new version of getting those information that doesn't exist in the base, but that's the contribution is only small token spaces. Most of the behavior that we found was it has a surface level modifications with no deep into what exactly those behaviors are in the model spaces. And what was found that the base model's capability was even better in a lot of cases compared to the capability of instruction tuned models. So this understanding sort of gave us an idea that there is a more thorough version of behavior is required and instruction tuning is not enough. So instruction tuning, the one thing that we found that it doesn't fill the knowledge gap at all. The model that was not able to answer the previous questions still cannot answer the current questions in some of the instruction tunings. And if you have really a deep reasoning capabilities, instruction models don't really follow the instruction that you really want to emphasize on as you go forward. So let's just talk about this in a very simple example of how this behavior is in practice works. So this is a very interesting example that we started looking at that I started with a query, which is I have been feeling overwhelmed today, and what should I be doing it? So what we started was, we started looking at the first behavior where we look at the persona extraction from this model. So what we saw that when the model is able to extract the persona, it is a good sign that at least it understands some part of the input query. Then we looked into a design where we asked the model to quantify the gap on this particular input. Now at this input, I'm not giving any additional context. It is still the original input of the input data, right? So what we found that when we look at the knowledge gap, which we used it through weighted contextual mutual information approach, we found that at least it is contributing to 85% knowledge gap. At this point, I'm not really eligible to give any meaningful answer to the end user, right? At this point, I'm looking at the feedback, which is not the feedback coming to the user, it's a feedback that the model is looking at from itself, which is nothing but a thought process. And the feedback is that this information is not sufficient enough to give a particular information. Now, what we looked at is, now, can I extract something from the persona that the model has extracted and try to extract some contextual information from the persona to give a particular information? Then if I look at those personas, I come up with a refined answer which says that I do not really have a sufficient capabilities of answer these questions. And if this feel like it sounds like you're going through a tough time, it feels if these feelings still persist, it might be helpful to speak with the mental professionals. And would you like me to refer to those resources? Now, this information that I'm getting, I can get in other LLMs as well, but now I really have an information of why this particular information was given to me at the first place. Because the gap is so huge that the model is not giving a particular response that is favorable to me or useful to me. So this design sort of gave us that, can we escalate this behavior across the mental health data set that we found and see if they can be used to get some understanding about it. So when we looked at this design into an automatic matrix, which is the blue score, rouge, and F1 scores, we didn't find any significant differences in the scores. So if you see over here, most of these information are roughly that remains the same. The reason is because the challenge was not in this final outcome that we are looking at. The challenge was here. So this part of the knowledge gap is something that we are not accounting for when we are evaluating the final responses, right? So that made us think that there is some sort of a new versions of metric that we can utilize for this behavior. So in this case, when the model is looking at this thought process, or when the model is looking at this set of personas, these behaviors are not manifested in the final response that is being generated. So when we started looking at another set of metrics which is built and not so evaluated, is the one was the GPT preference, and the other one was the Nubia. So Nubia is a pretty interesting metric that allows you to investigate what is happening inside the model's behavior in terms of the coherence, semantic relevance, and more intrinsic phenomena as compared to Blue, Rouge, and the BERT F1 scores. So we extend this work a little bit further to see that can I pair up my generator with an evaluator? Now, why do I pair up these two information? Is because I have an input, which is nothing but my chat conversation happening in the end user. And these are my sampling responses that I'm giving, sample 1, sample 2, sample 3, and sample 4. And part of the evaluator is essentially nothing but a mechanism that is evaluating whether the outcome is relevant to the user input, whether it is a conversational engaging responses, whether it's a contextual appropriate responses, and so on and so forth. So what is this new series of 6 points that we have introduced in the evaluator? So this new set of points actually came from the way this metric was developed, which is evaluating this engaging behavior. And also what we found that when these informations that we have evaluated, that we have modeled as intrinsic components, we want to test these components as they are in progress, right? So we want those to be evaluated as well. So that's why the only thing that you can do with this behavior is to stitch your generator with an evaluator. And consider this phenomena to be very similar to GANs. It's just that you do not have a discriminator, you have an evaluator at the other end, right? So evaluator is trying to test that which of these responses are meaningful for the final outcome. So this behavior, this twofold direction is sort of an interaction between an evaluator and a generator behavior. So this structure on the same set of a metric showed us that with the LLM evaluator, I'm able to have a better improvement, slightly better improvement over the standard metrics in which we were not seeing evaluation improvement in the previous segment. And now with the human preference matrices, which is GPT-4, Nubia, and human performances, we do have a relatively better improvement of 52%, which was way before less than 50% in the previous case of evaluation. So this design of a human of a LLM generator and evaluator seems to be an interesting strategy to evaluate each and every individual steps that the LLM is following when it is giving you the final responses. So with this behavior, I want to summarize some of the core works that we talked about in the neurosymbolic space. One was that we looked at the definition integration, which was the first work of Well Done, where we look at the definition is possible in a simple and intuitive way of integrating your external knowledge into the LLM spaces. The second thing that we found was the rule of thumbs or of extraction and contextualization was an effective way of telling the model to be consistent with the knowledge it is being or with the data it is being trained on, right? The third component that we looked into was the weight matrix as another way of integrating your models, steering your models in the direction where you really want it to be, right? So this is semantic encoding and decoding optimization. If you want to see it right now, is going to be more like the sparse autoencoders that are being used for doing the mechanistic interpretability. So sparse autoencoders are nothing new. They are sort of an external weight matrix that is being used to glean insight into what the LLMs are seeing or LLMs' attentions are being depicting. And the last part, we looked at how the workflows of or the questionnaires can be a part of your models. We don't really need to drive by knowledge graphs. We can even translate this information into using the workflows as well. And finally, we covered up with the knowledge gap, which is another way of investigating how knowledge can be incorporated, where, when, and how the LLMs can also give you information about where it knows the information, where it doesn't know the information by knowledge gap quantification. And you can resolve those gaps by stitching the generator with an evaluator framework. So that is an interesting design of turning into the neurosymbolic spaces. So with this, I hand over to my next presenter, Edward Ruff from Booz Allen, who would be talking about vector symbolic architectures for neurosymbolic AI.
Thank you, Minas. Hi, everyone. So I'm going to be talking about vector symbolic architectures, which is good because that's what it says on the slides. This is a set of techniques that generally falls into the category of good old-fashioned AI, started back in the early 90s, and was an approach to join connectionist and symbolic reasoning at the time. And so the goal was that we want to build sort of first-order logic-like systems on top of real-valued vectors. So intuitively, and especially the arguments back then and still echo now, is that symbolic systems give you provability, they give you exact results, that you know what you're getting, but they're very sort of rigid. If something is a little bit unusual, it doesn't fit in. It has to fit the exact rules. Connectionist approaches, deep learning, have really excelled in this fuzzy regime where things don't quite fit, and just throw lots of training data at it. Let the model figure it out. And we want to sort of hybridize these things. And VSAs, also called hyperdimensional computing, the HDC folks normally are coming at it from more of a hardware-oriented view. People who call it VSA are normally coming at it from a more machine learning kind of view. There's another name of it called semantic pointers, which is people looking at the same thing from a cognitive scientist point of view. So many different points of view and different communities working in this area. And it's still an active area. And so what is it? So here I've got this beautiful picture of a corgi. And we can say the corgi is represented out of multiple components. It has legs, it has a body, it has a head. And this can be hierarchical. Well, a head isn't just its own atom. A head is composed of a mouth and a nose and eyes. And so VSAs are going to be real valued vectors that allow us to sort of build these kinds of relationships. So we're going to have a set of primary functions. I'm going to focus on one primary type of VSA. These can change a little bit depending on which one you're using, but this will be sufficient for our purposes. So you have addition. Addition is regular vector addition. You're just adding the values in the vector together. You can think of this kind of like an OR operation. I'm combining two things. You can have binding, which is sort of like and, like I'm assigning these two things together. They are now intrinsically linked. Permutation, you can think of this as repetition. So I could have a vector representing position 1, and I can permute it to get position 2, and I can permute it again to get position 3. And finally, we're going to have a similarity function, which basically is usually cosine similarity. Again, this can change a little bit depending on which VSA you use, but it's going to tell you how similar two vectors are. And these, annoyingly, this doesn't show me my slides. There's a very little tiny picture of my slides. So I might have to look to the side a little bit to make sure I get the math right. So these are our primary VSA operations. And imagine you have the sentence, the red cat and the blue dog. If you use word2vec to embed each of these words into a vector and then add all those vectors together, that's like a very common thing to do today, but you can't distinguish order. You can't tell which animal was red and which one was blue. If you use binding, you can do this. So I can bind red with cat plus blue bound with dog, and I have a new singular vector which distinguishes red cat and blue dog. I can figure out which one's which. And if I did blue dog, red cat, I would get a different vector. One of the properties that most VSAs maintain is quasi-orthogonality. So if I take two arbitrary vectors, they will be their similarity will be approximately 0. Why quasi, not just orthogonal? Because if I mandate orthogonality, I'm limited to d items for my d-dimensional vector. If I give myself some wiggle room, because part of the point is to hybridize symbolic style AI with connectionist, I give myself some wiggle room with quasi-orthogonal, just be approximately equal to 0. And now you can store many more than d items in a d-dimensional space. You pay some price with noise. We'll talk about that a little. This quasi-orthogonality also respects binding and permutation operations. So if I bind two items together, their result is dissimilar from their inputs. This is important for me to be able to successfully build larger data structures on this foundation and to successfully run it without noise just sort of overwhelming the system. You can also invert vectors to sort of unbind something. So I have a sentence vector that represents the red cat and the blue dog. I can ask what was red by unbinding with the vector for red. Depending on which VSA you use, how you define unbinding is a little different, but that's fine. But now, everything I've told you about gives us the foundations to start doing weird, interesting things. So I can do the red cat and the blue dog. That's a sentence. I can ask what was red. I can ask what was blue. I can ask, is there a frog in the sentence? And I get something approximately equal to 0. So no, there's no frog here. I can create data structures. I can have X represent a position in a list. And I can permute it over and over and over again to get different positions in the list. This is now also a list that can represent empty things. It's also an infinitely long list because the list is initially empty, the 0 vector, and I can permute something 4,000 times and then insert by binding just that one vector. And now I have a list that's empty except at position 4,000. So now you can start to do really weird things. I can ask what's the second thing in the list? I permute twice, I unbind, and that gives me a vector approximately equal to whatever was in the second position in the list. If there was no second position in the list, I'll get a vector approximately equal to 0. So this is a really cool foundation now. I can start to get creative and come up with ways to represent a lot of first order logic constructs I might want to perform in entirely vector-based operations. And then on the other side here, there's lots of different VSAs that have been invented over time with different little properties and trade-offs. And this is my favorite mathematical property. And no, you're wrong. This is my mathematical favorite property. We're not going to get into all of those. That's fine. They exist. They're lovely and all special, unique snowflakes. I'm going to talk about one primarily called the holographic reduced representation, a name that confers a desire to sound very complicated, but it's not as complicated as it sounds. If you go read the original paper by Tony Plate, it's an intimidating looking paper, but aggressively readable. So what we're going to do is we're going to define our operations for this specific VSA. Our binding operation is going to be the element-wise multiplication in the Fourier domain, and then we sort of go back again. So this is also equivalent to something called a circular convolution, but this is much faster than convolving. This is d log d time instead of d squared time. So don't actually do a convolution. Our inverse operation, we again just do the FFT, and then we take the reciprocal of every element and go back. The HRR, as it's called, or abbreviated, has an inverse operation and a pseudo-inverse operation. The pseudo-inverse operation exists because the mathematically correct true inverse is numerically unstable. And so they came up with this clever pseudo-inverse that involves just shifting everything over by 1 that is approximately equal to the true inverse. And some of the work that we did, we added a projection step. So when we initialize our vectors, you project them onto the complex unit hypercube so that the true and the pseudo-inverse are mathematically equivalent. So we sort of have this constraint so we can use the cheap pseudo-inverse and get the same result. So how does this get us these properties I described before? Let's walk through. So we're going to say we have a three-dimensional example. We've got a vector C and X, and we're going to unbind with C. So we've got the dagger for our unbinding operation. So let's actually write out these vectors. And if you write out this product, you get this sort of ugly matrix. I'm going to make this less ugly for you, don't worry, because I'm not good at math either. So I'm going to highlight a set of red and blue values in this resulting matrix. Now, a key thing in almost every VSA is how do you initialize the values in your vectors? What HRRs do is they initialize them from a scaled normal distribution with a mean of 0. It's really important we have a mean of 0. Why is that? Well, if we take the red values and we're adding up all their squared values, if we sort of get clever and subtract a 1 at the end, we're going to get a new random variable that has a expected value of 0. And if you look at all the blue values, we're just taking lots of, remember, every individual value is sampled from something with a mean of 0. So multiplying by expected values of 0 gets you 0. Adding expected values of 0 to 0 gets you 0. So all those blue values, which we're going to rewrite as eta, also have an expected value of 0. So we can rewrite this result as 1 plus, I forget that Greek letter, x plus eta. Both those terms have expected values of 0. And so the expected value of this whole equation is the original value x. So this is to convince you that these weird quasi-orthogonality properties that we talked about at the beginning are actually obtainable. And here's how they work for one particular example. And this gives us the foundation to start doing weird things. So a lot of what we've been working on is trying to bring VSAs into the 21st century. So VSAs were classically done by people thinking very hard about clever little data structures and algorithms, and oh, you do this in this order and you do this way, and it'll create this machine that you turn the crank and it does the task. But I'm lazy and dumb, and I just want to use gradients. And these are defined over real valued vectors. So I should be able to just differentiate through this whole thing. And what I would like to do is I'd like to use VSAs as a way of specifying symbolic priors that I want to encode into my problem or model. Because this is basically giving me a differentiable form of first order logic. So let's pick some examples that are fun. A first example is a task from extreme multi-label classification. If you're not familiar with this, you have an input X and you're trying to make a 0-1 binary classification task, except you have like a million binary classification tasks that you need to do based off of one input vector. And no one wants to train a million models and run a million models. So you want one model to do a million different binary classifications. This is used a lot in advertising. You'll see a lot of papers from Amazon in this space because they're trying to make money and sell you things. And okay, so this is a lovely good task. And what we're going to do is we're going to assign every possible class that might be predicted as like present with its own VSA vector. And those are going to be C1 through CL for L total classes. And we're also going to define special vectors to represent the concept of a class being missing and the concept of a class being present. A key thing about XML problems, we abbreviate it with X instead of an E because we're cool. But a key thing about XML problems is that most classes are not present most of the time. You will have a million predictions to make, maybe 10 of them are present. So it's a pretty sparse activation pattern for your classes. We will exploit this. So what we can do is we can create a symbolic loss function that captures the knowledge of this problem. Because when you're trying to build an XML model and you've got a million outputs, just that final like linear layer at the end of a neural network will be like 1/4 of the network. It's a massive linear layer to have. It's unwieldily large. It takes a long time to train. It's very painful. So can we replace that giant multi-gigabyte tensor at the end with something smaller using HRRs? And we can. And so what we do is we create a sentence or statement vector that is every class that's actually present in the true label bound with the concept of present, plus every missing class bound with the concept of missing. Now, at first, this seems useless because I'm still iterating over a million things. But we have symbolic properties of HRRs and VSAs. So they're distributive, so we can move the binding of present and missing to outside of the summation, and it's still mathematically equivalent. And we can just add up all the vectors once into a vector called A for all of them, so that instead of adding all the classes that are missing, we can just subtract the 10 classes that are present. So remember, this is a very sparse activation set. So now instead of doing a million operations, I'm doing like 10 operations. And my loss function, I'm going to compose by taking all the things that are supposed to be present, unbinding them using cosine similarity, and seeing, can I successfully unbind all the things that should be here? And for the missing things, I'm just going to take the vector representing everything that's missing and try to unbind that and see that I can't find it. So I want to see that I can find things that should be there, and I want to see that I cannot find the average of missing things. I can do all of this in like 10 operations in a much smaller dimensional space. So we were doing this with tests where we would use at most E equals 3,000 dimensions to literally represent around 1 million classes which again is why we need quasi-orthogonality, because otherwise there would be no hope. And on the right-hand side is the table of results. And we were saying that generally we got often improved results near state-of-the-art, or just something that was otherwise very simple. We just had simple, and we tested this with fully connected networks, with LSTMs, with convolutional networks. It worked with all of them. And so we have sort of now shown a cool hybridized example where we used VSA's symbolic logic to specify a prior, differentiated through that prior about how the output space is going to work, and then successfully make predictions. Let's keep going. These are just some results. I'm going a little slow, so like here I'm just showing that the network was much smaller using HRRs instead of doing the naive approach, EAS. So let's go to another fun example. So let's say that you want to deploy your neural network onto some third-party platform, something like AWS or Google Cloud or something that's going to run your model and run your predictions all over the world. But you don't fully trust them not to peek under the hood, right? Like someone's sending data to your model and someone's like, oh, you get so much traffic to your model. Maybe I want to go look and see what your model's doing. Maybe that's something I want to make a model for, right? That's not nice. That's not good. And like, man in the middle of the tech, they're the man. Like they could figure out a way to peek under the hood and find out. So how can you deploy your model on this platform without sort of giving away the goose while still getting some predictive utility? And we're again going to exploit a nice property of VSAs that when you bind two things together, the output is dissimilar from its inputs. So here I've got the input image A, it's a beautiful flower, and I'm going to create some secret, kind of like a one-time pad, but not truly a one-time pad because I don't want the cryptography people to get angry at me again. But let's call it a one-time pad for simplicity. I'm going to bind it with my input A, and I'm going to get the output B. Can anyone here tell me that that is a flower? No. But I unbind with my secret, and I get the retrieved image C. Ah, yes, it's back where it was again. So can we use this for our predictions? And because we're using a Fourier transform for our HRR, we can pretty easily generalize this to images by just saying we're going to do a 2D Fourier transform. And this will just sort of work quite naturally. So we came up with this fun title that avoided using the word encryption so that we wouldn't get matched encryption reviewers, called Connectionist Symbolic Pseudo-Secrets, CSPS. I had a lot of fun coming up with the name. And here's our approach. The left and right-hand sides is when we have control. And we're going to do training is all locally. We're only going to try and protect deployment. Protecting training is very hard. So we're just only going to protect deployment. But so we have our input images. We bind them with secrets. We have the secrets. We generate them locally. And they're VSA vectors. They're just random vectors sampled from the void. We have a UNet network that is sort of the backbone that does the feature engineering or the feature extraction. And then when we're training, we have two losses. One loss, we compute by first unbinding our secret, and we have a little teeny tiny network that just quickly makes the prediction. Because again, we want the third party to do the majority of the compute work. Otherwise, there's no point. Our second loss, again, a small network is going to make the prediction, but we're going to change the sign of the gradient so that if the model is able to successfully extract information to make a prediction without the secret, it's going to alter all the weights of the network in the opposite direction of being able to do that in the future. So we're simultaneously training it to require the secret to be able to make the prediction by being unable to make the prediction when it does not have the secret. This works pretty decently. So the approach a cryptography person will tell you for this problem is to use homomorphic encryption because it is real encryption and it does the thing. It is also unbearably slow. We will all die from the heat death of the universe before it's done. So we have like estimated runtimes, and these estimated runtimes are for a single layer network, not even a multi-layer network. But on the right, we can see our classification accuracy, and it runs very quickly, which is good. And we can repeat this multiple times if we want to increase accuracy by just generating more secrets and pushing it through the network or through the provider multiple times. And there's ways you can do that very efficiently by sending one package. You don't have to send 10 different transmissions. And there's no way for your provider to know if this is one thing 10 times or if it's 10 different things. So it's accurate, yay. Do you actually get any data savings or compute savings? Yes. 2/3 to 3/4 of the compute is done by the remote third-party platform, which is good. That's the goal. Are we giving away any secrets? Like, this is all pretty heuristic. I was kind of hand wavy about like proving that it works because I'm not a real cryptographer. So we tried very hard to break it, and we couldn't. So we're looking at the adjusted RAND index for the outputs and inputs to the network. So is there anywhere that we're leaking information about how many classes there are? And adjusted RAND index, values of 0 is random labeling. Values of 100 is perfect classification. Values of -100 is perfect anti-clustering. All values are near 0. We appear to be doing a good job hiding this. What if we make the adversary even smarter? What if we go really crazy and say the adversary already has our entire data set? And so they can just train their own model from scratch to predict the true label from our encrypted inputs. This is a very silly adversary because in this scenario, the adversary has already solved the problem, but is then trying to attack us anyway. And under that constraint, they're only able to do mildly better than random guessing. 19% over 10% for random guessing on MNIST, 4.6 over random guessing rate of 1% on the ImageNet, over an unreasonably powerful adversary. We also tried some adversarial machine learning techniques. Does PGD work against it? No. The images all look like gobbledygook. Can you train an autoencoder to do it? No, the images all look very blurry. So this is all quite good. So let's do, oh, my slides are advancing automatically without me. How helpful. So that's connections to some symbolic pseudosecrets. Let's be weird again. Let's say you're interested in self-attention and LLMs because self-attention is all the rage right now. Can we recast the logical explanation of how self-attention works using HRRs and then get better results or get some benefit? And the answer so far is yes. And so if you're not familiar with self-attention, the equation is in the top left. It's a very obtuse equation, but the way that it is generally explained is you have queries, keys, and values, and you're basically computing a kind of fuzzy dictionary lookup. You have some sort of match between the queries and the keys, and those go into the softmax, which gives you a weighted sum over your values. We can represent all of these concepts inside of a VSA. We can construct a sum of queries bound to keys. We can then check if a key or is present or not with unbinding, and then we can compute a softmax ourselves as we so desire. So hypothetically, this is a way we could avoid the quadratic complexity of computing self-attention using the log linear complexity of the Fourier transform inside of a VSA, or inside of the HRR specifically. So let's draw this out a little bit more on the diagram size little toy version of the logic of how self-attention works. And so we're going to construct our dictionary of key value pairs by binding every key to its associated value. This is collapsing the entire key value matrix into one single vector. Pretty heavy level of compression. And then if we have a query, we're just going to unbind with that query and see if it's approximately equal to 1. Yes, it's present. Or is it approximately equal to 0? No, it is missing. And we can implement that. It doesn't take that much code. That's the entire sort of bit of code. We can do multiple queries at once by just sort of summing our queries together and then unbinding the sum of the queries. And then we'll normalize with softmax as people do before. And then our final attention is just going to be the softmax scores W times the corresponding value vectors. And this, my student Mohammed turned to her former. And you might notice that in this case, we don't have any vectors that are sampled from the distribution that is expected from a 0 value distribution. So why would this work? Well, when we write out what's happening, we end up with 2 terms or noise terms that, regardless of what you're querying, are of approximately the same magnitude. And the softmax is a function that is invariant to transformations by a constant value. So by using the softmax, we are effectively denoising the noise we introduced by not having the correct input distribution of our vectors. So we got this, we weren't so clever to like realize this at first. We sort of did the dumb thing and then it worked, and we were trying to figure out, well, why does it work? And we realized this was what was going on. And this works quite well. So the long-range ARENA benchmarks, multiple classification tasks for very long sequences where people have been doing all sorts of different transformers. And most transformer alternatives that have been published tend to do worse than just a regular transformer in at least one of these benchmarks. So I highlighted those in red. At the time that we did this, ours was the only method, along with this Luna 256, that was not worse at something compared to the original transformer. Luna 256 also does, the way Luna works is it creates a just sort of naive projection into a very low dimensional space and just uses that. So Luna does struggle if something has a lot of context sensitivity, or has a lot of information that's needed across the entire input in order to make a successful prediction. We'll come back to that. We can take our softmax attention scores and visualize them to see what's going on. So one of the tasks is to do basically CIFAR classification by seeing the pixels one at a time. And when we visualize our softmax attention, we see that the network is successfully learning the 2D structure from a 1D sequence of pixels, which gives us further confidence that, yes, our weird approach is actually learning to do something pretty cool and useful. And it's also very fast and very low memory. So the size of the bubbles is how much memory is being used to train the model. And the x-axis is speed. Examples per second is more. So you want to be further to the right of the plot, of your right plot. LRI benchmark score is the y-axis. You want to be up higher, so you want to be in the top right corner where we are. That's our dot. Yay, us. You can see our dot is much, much smaller because we're using a lot less memory. It's also very fast for making predictions. And so you can see here the time that it takes us to do a batch size of 48 seconds, is faster than the per item time of the transformer at a batch size of 32. It's the per item time, which is why you see the time decreasing as the batch size increases, because you're getting better compute efficiency as the batch size increases. We did this work because we're interested in malware detection. If you have a binary executable and it's 200 megabytes in size, that's not that big of a binary. That's pretty normal. If you view that as this is a sequence of 200 million bytes that I need to make a classification from, that is a very obscenely long classification problem. And here we see that our HRR former generally performs the best, is much faster. But 2 key things to note. One, you'll see Luna 256, what was originally the best or second best, that had no weaknesses in the long-range arena benchmark is the orange line that's performing the worst in terms of accuracy on this very long sequence problem. Because this problem is like real-world malware data where there's a lot of information over the length of the sequence, and the Luna strategy just is not amenable to it. The other key result on the slide is the FNet results, which are also considerably worse. What FNet does is it replaces the nonlinearities by doing a FFT and using the FFT as its nonlinearity. So this is a really useful result to tell us that our success is actually coming from the sort of neurosymbolic interpretation of what we're doing, and not just a difference in the nonlinearity that we're using. Because if it was just that we're using an FFT, we would expect to see FNet perform much more closely to our method, because there's not that many more steps to ours than just doing an FFT. I think I have 5 minutes left. Is that right, Manas? All right, I have more slides. I'm not going to go into them really because I can't fit them in 5 minutes. But if you want to support my ego and vanity, the last thing I was going to talk about was a new VSA we developed by basically rederiving the HRR, but replacing the FFT, because it's got some numerical instabilities, with a numerically more well-behaved alternative, the Walsh-Hadamard transform. And we did this so that we could hopefully have a VSA that's both good at classical VSA tasks, but also good in differentiable applications. And that's what we generally saw. So here's plots of a bunch of classical VSA tasks, and we generally see our HLV, the Hadamard derived approach, performing quite well compared to alternatives. And then we redid our XML experiments and others with our new approach. And we again see that it does better in deep learning applications as well. So we enable numbers for us. And yeah, close enough. Any questions? Got like 3 minutes if someone has a question. Yeah.
You mentioned in the beginning.
Oh, there's a microphone in the center if you don't mind using it so everyone can hear you.
Hi, so my name is Lupio. I'm from University of Porto in Portugal. You mentioned in the beginning the example of the parts of the dog.
Yes.
And so I was wondering how do you train this for having this kind of grounding with parts of images or in terms of images? So that's what I understood. And what kind of training you use, and is this approach better for that?
So this was more of a motivating example. We haven't done this specifically. It's been on our to-do list to try it. In terms of where my head's at, I've been thinking of there's some work by Alex Graves back in maybe 2014 on LSTMs with dynamic amounts of compute, where the model itself figures out how many steps to do. Similarly, there's some of the early work that preceded self-attention that looked at how to have a neural network attend to different subregions of an image to not look at the whole image to make a prediction. That I would be using as ways to sort of say, like, extract a VSA from this component of the image and try to combine them together. So I don't know how to do this for computer vision yet, but I think where we've been trying to push for is that that's a possibility and an avenue to explore, where a lot of old VSA work was very hand engineered. So Chris Elias Smith has done a lot of really good work in this space from a cognitive science perspective. And he's got a very complex VSA machine for trying to simulate like a human brain at doing cognitive science tasks, where like they can make it go through like an IQ test and solve like Raven's progressive matrices. but it's all hand engineered. I don't have the time or intelligence to kind of do that hand engineering. So this is where I want to get to, is how do we make systems that do this kind of extraction and hierarchical construction automatically. So that's more the dream. Was that helpful?
Yeah, okay, thank you.
Very much for the talk. So I have to admit I didn't quite understand how you mix BSAs with learning, like with deep learning. Mm-hmm. So first you start talking about BSAs, like having a vector, like a continuous representation, I suppose, for every concept, and a set of rules that are differentiable with adding, with indexing, and all of these things, like permutations. But when you want to learn something, for example, you put the example of extreme multi-level classification. Mm-hmm. How does that specifically come into play? So like you learn, let's say, using backpropagation, like a vector representation for each concept, but then in your network, you have like this operation with a semantics given by BSAs? Or how is it? Sorry.
So it depends. So like the XML example here, we're basically constructing a loss function out of VSAs. And so the construction of the loss function is us specifying like, hey, here's how this problem works and how you know if you're doing good or bad at it in a way that would be hard to write a loss function for normally. And then because it's all mathematical operations, we can just auto diff through it and calculate a gradient through the VSAs into the neural network.
Yeah, but for example, what are you learning? So you say that you have a set of operations you're back propagating through them, but then what is the network exactly learning?
Are you asking like can I go back and reinterpret the weights of the network and like say that this is what this weight is doing, or are you asking if I can interpret the process of the network?
So I'm asking, sorry if I don't quite understand like the foundation for, so imagine you have like the standard so a standard network, and now a network with BSA that you said that in this example you would have, I think the last layer was like substituted by a different thing.
Yes.
So basically in practice, you substitute the final layer and you use a different loss function.
In this example, yes. In the transformer example, we use a normal loss function, but we replaced self-attention with something that was designed or defined via VSA operations. So in terms of like, there's still some amount of like the black box of neural network, like you learn with gradients, what did it do? I don't know. But in terms of what's the process being done, I've manually specified the logic of the process.
So I guess that you have like this mathematical framework BSA, do you specify the process, like the set of operations that follow like a specific semantics? And when you train a system, like all the different parts are learned, like for example, the vector embeddings or like the weights, whatever, you know that it will follow these BSA semantics and have these properties.
More the latter, yes. Right now we're sort of using the VSAs to define the set of operations, but we're not learning how to combine the VSAs. I think that's super interesting future research, but not yet where we're at. So right now I'm going to define something. I'm going to define some set of rules with my VSAs. These rules are differentiable, and I can interpret the logic of what I've done.
Like for example, attention, that you formulate attention, you say, okay, this performer is actually performing attention, not something else.
Yes.
Right? Okay.
Yeah. So it gives me something that I can interpret and I can understand and sort of specify more complex desires of the network, right? So the VSAs are sufficient to specify generally a first order logic, which is like a technical sort of set of statements that can be represented. So if I can think about what I want to happen in terms of first order logic, I now have a way to convert that into a differentiable unit for the network. But I don't have a way to introspect like mechanical interpretability is like one of these areas of like trying to introspect into like what did it actually learn? I can't do that yet.
Thank you very much.
Thank you. And then, did we have a break, or am I handing off again immediately? Enough. Thank you so much.
Hello, everyone. I will be talking about grounding black box language models with retrieval augmented generation. So this is about how does the language modeling start. So we started with a normal Turing test. Then came ELIZA. ELIZA was the first mental health language model, which was introduced in 1966. Then we are in the era of ChatGPT now. So the first of the models, like the symbolic era, pre to 1990, where we worked with like rule-based modeling, expert system, which have like the limited generalization. Then statistical era, 1990 to 2006, we worked on data-driven approaches and probabilistic models. Now we are in the scale era with lots of data, large language models, deep learning, and like all these models which have like massive computation power. So the earliest one was ELIZA, and it was developed in MIT. And ELIZA worked with like a conversation by rephrasing the user's statement and asking that if a mental health condition can be analyzed or not. Now we in the era of the LLM, which we have like lots of data, lots of information, and lots of computation also. So we all know about word embeddings, how it worked. So it is like the discrete representation of the words and vectors, and it is useful for cosine and Euclidean distances. And we can do it by normal models like word2vec, Glove, BERT, Elmo. Then after that, we came up like recurrent neural networks, long short terms, long LSTMs in a way of representing semantics in a sequential way. And LSTM do not inherently capture symbolic or structured knowledge, making them less effective for explicit reasoning in grounded AI applications. Then the era of transformers came. Transformers focus on like what the model sees, and it focused basically on the attention layer, which was helpful to generate the output. But these also have some limitations. Then I will talk about like how all the data preparation works in the LLMs. So typically we have to start with a raw corpus, and then we have to do a lot of quality filtering, which is not being done in training any of the LLMs currently. Then we have to do all the privacy reduction, tokenization, and then only we can train our LLM models. Now, what LLMs can do? So earlier eras, when it was in 1990, LLM was able to help in very specific tasks like statistical models, probability estimation. But now, in this era where we have models like OpenAI, GPT, where we can use LLMs for general purpose tasks and use LLM as solver for many of the problems like summarization, scaling, language model scaling, and solves various real world tasks. For doing those tasks, we need prompting. So this is an example of few-shot prompting where we have to provide some examples, and then we can get output based on those examples. Another type of prompting is chain of thought prompting. So chain of thought prompting is used for reasoning. Now, how it is related to grounding, that it does a shallow kind of grounding, but with reasoning. It is not completely grounded in their responses, but it can able to do a shallow grounding. Then we came from prompting to fine-tuning. Fine-tuning is kind of training a model to ground to its domain by updating weights for specific domain. But still, it is not very specific. It cannot do grounding in very specific way for domains which like law, legal LLMs, and all these things. So this was in 2024 when one of the famous Harvey AI company startup built their custom trained LLM using OpenAI, and they claimed that they were able to reduce the hallucination because it was like 10 million token worth of data, and that started this case law firm, and they are now working on with this LLM Harvey AI. But why the need for trustworthiness in generative AI? So this is an example I was trying on ChatGPT when I was asking that, hi, my name is Deepan, how many E's are in my name? So it was able to provide that you have 2 E's in your name. That was easy reasoning for sure. But when I ask like a mathematical question, 9.11 and 9.9, which one is larger? Now it answers that 9.11 is larger than 9.9. Now, what is the reason behind that confusion? It is due to tokenization. When you do tokenization of these things, so 0.11 will always give a higher value than 9.9. You can also try it out on this app where you can see like tokenization values of these things. Now, if we go, we have been always known many news about generative AI. So this is one of the news which came up in 2022, the story of lawyer who employed the ChatGPT, and it was about the trust issues. So this lawyer used ChatGPT for generating citations for the case law, which actually did not appear to be true. But now that ChatGPT asked the LLM that provide me some citations, and that citations he quoted in the case, and those at that time that lawyer faced issues of like claims that were false, but they claimed it as true claims. So that is the problem where the trust issues remains, and LLMs cannot be used without checking out the true citations and then using it as like a proper report where we need claims to be verified. So this is our current work, which is gonna be appear in a book chapter, Neurosymbolic AI for Legal AItrism, where we talk about how we can use neurosymbolic AI for trustworthiness, reliable, interpretable, and safe models. So how we can do that is we can define our neurosymbolic symbol, and if a user can ask any question about any legal query, then neurosymbolic AI will able to answer it properly by retrieving the top K documents, like the top K claims of that user query, to answer with a proper attribution from the data set. How we can do that? So we have to define a knowledge graph for defining a legal domain knowledge graph, which have all these things like claims, mentions, and how much of the claim it was, and it was against or it was for. So these kind of things we can define in a proper legal knowledge graph, and then use that knowledge graph for citing that claim in the generated answer. But there are more challenges with the generative AI. So the challenges are that it is inconsistent. It is nearly impossible to reason like why did it generate those answers. Prompt injections can leak our data. Context windows are still small. Then bias, because the training data was not clean, so there will be bias in the data, and reliability issues. If reliability issues like if you ask a chat GPT right now, like what will be the case outcome for this thing, so it will give you different answer. But if you turn off it memorization power and ask it again after some time, it will give you the different answer again. So that's the motivation that why do we need grounding? So if we see grounding definition in terms of source attribution, so every claim in an LLM response should generate verifiable, well-grounded, and answer with a proper knowledge base, retrieved from a proper knowledge base. So in the source attribution domain, we can define 2 approaches to ground AI. First will be grounded generation, which is like enhancing AI with verified knowledge. And the retrieved facts are from the proper knowledge base. The knowledge base is being created by by verifying each of the knowledge from the databases, and then it is an intrinsic phenomenon. Sorry. The second approach is to grounding verification, where we cross-check each of the claim with authoritative sources, apply fact-checking models, and it is an extrinsic phenomena which is done after we generate our answers. So this is one of the example from our work where a user is asking that this is a post of a mental health, and how do we classify this post? So it should answer with like emotionally damaged and traumatized, but it is not actually giving that kind of answer. It is just giving a generic answer. The motivation of doing this work was the recent character AI work. And I hope you are aware of the character AI, that a teenager have been consequences for asking the LLM about mental health question, and those consequences are not recoverable. So this kind of work where we do the grounding generation, that asking inputs about the mental health, but it is not giving any generic answer. It is not able to understand the sentiments of the user. And the other example for the grounding verification is that the data is mismatched. So the input to the Google is that what is the target blood pressure for men? And Google Gemini is basically mismatching the values. So if we see in the published article, it is like 130 mmHg, but in this, it is saying that 130 to 139 mmHg. So the verification here fails when we use LLMs. Now, how we can do this type of grounding is by two. So we discussed in our earlier talk, symbolic grounding and functional grounding. Symbolic grounding must retrieve, recognize, and structure the information correctly before using that grounding. And we can do it by two ways: retrieval augmented generation and knowledge graph based grounding. Another one is functional grounding. Functional grounding should reason, verify, and adapt responses according to the context. And we can do it by attribution-based grounding and interactive and reinforcement-based grounding. Let's see symbolic grounding. So retrieval augmentation generation is that we all know that the knowledge is cut off for all the LLMs currently, and we cannot update these knowledge bases on day-to-day basis. So we enhance our LLMs with retrieval-based system using external knowledge database. But so these have some advantages, that RAG is like accessible, affordable, safe, cost effective. We can do these kind of systems for specific knowledge. We can custom train, continuously update, easier to customize, and then fact checking also. So this is an example from our recent work, Reasons, a benchmark for retrieval and automated citations of scientific sentences using public and proprietary LLMs. So what we did is source attribution. What is source attribution? We try to retrieve, recognize, and then attribute a specific scientific claim. So the motivation behind doing this was, we all are researchers and we need to write related work for our research papers. Now, if we write something, if we want to cite it, so we have to Google it, that give me the citation for this kind of sentence. But what if there is a system which will automatically cite that sentence from the data set available? So we try to do with LLMs that we are giving a query that this is the sentence and this is the paper title of that sentence. Can you provide the author names? Why we wanted to provide author names? Because if we want to see that if there is relevant work for relevant work to that sentence with that author. That's why we want author attribution here. But now most of the LLMs failed here, that it is not able to give up the author citations after providing RAG also. So we have to fine tune our cross encoder for RAG model to provide a correct answer. Let's look into more detail how we did the symbolic retrieval based grounding. So we start with the instruction that I have taken a sentence from a research paper title. This is our source research paper title. Give the title of a possible research paper that is cited. So we are asking that given a sentence, give me the possible research paper titles. It means that suggest some titles which I can cite in my research paper. So we started with paper title, a sentence. But initially, like we asked to the Mistral model, it passed. So we have to adapt. We have to adapt with a new type of prompting, which is sequential, indirect, and direct prompting technique. So how we do that? That we provide a metadata with it, an abstract of the source research title paper. Abstract is providing just more information about the paper title which we given so that it can understand the context. But now abstract can also be semantically same with another kind of abstract. So it cannot provide the ground truth validation that that paper is needed. So again, we add a further step that if the model is passing this information, we should add another kind of metadata, that is author names. Why author names? Because author name will make sure that this is semantically same, and then the author names should also be this for this abstract, so that it should not be semantically same with the other kind of abstract. So that's why we do another metadata layer of authors, and then we were able to get our ground truth for the given sentence. But there are few limitations with this approach, that it needs existing database, it have latency issues, hallucination still exists. There is a limitation of context length in the models which we are using, and it's dependent on the semantic search. So this is one of the example where our model fails. Like we are asking author names here. We are not asking title here. We are just asking the author names. So for asking author names, if you see Llama failed, then Mistral also failed. RAG and normal, like naive Llama failed. The RAG plus Mistral only gave 3 of the names, but so this one, Chi Wang, was not in the initial list. So it's like a part of it is correct, but a part of it is wrong. So we cannot consider it as a true prediction. Perplexity is a search-based engine which is used for attributing, basically identifying the correct information of a given sentence and finding citations. It also failed. Then we used advanced RAG plus Rama, which is also failed. Now advanced RAG plus Mistral was here correctly predicted this one. In advanced RAG, we have trained our cross encoder for our reasons data set. So that's why it was able to perform well. But this problem, this have still latency issues. So this was the time taken for all of our domains which we covered. So we covered 12 domains, and out of it, like 7 of the domains took like a lot of time in doing these kind of experiments. That's why we need knowledge graph based rounding. So what is knowledge graph? Knowledge graph is we can show our data in entities and entity types, and there are various forms of relationships in the form of ontologies, lexicons, and labeled properties. Now, how it can be related to grounding, because knowledge-based grounding basically save the information in graphs and link the concepts to improve the AI system's ability to retrieve and generate meaningful responses. So this is an illustration of ISEEK paper, which was published in 2020. And if we provide with a query, that query is about like, give me a description more about the including GDP inflation and influence on the employment. Now, this query can have several steps to reach to a conclusion. So it will do first constituency parsing, then it will do the stepwise layer, like what information does it needed to be extracted. It will go into the knowledge graph and then identify the important information like inflation, economy, and employment, because these terms were mentioned in the query description. Now this again, these also have like the subgraphs which have all the information about semantic query expansion. Then it will do the semantic query expansion, and it will send this knowledge graph to encode and sentence but encoder. Also, it will retrieve information from other knowledge forms like Wikipedia. From Wikipedia, it will verify its information, and then it will result back to the user. Like, do you want to know more about the gross domestic product, or do you want to know about the unemployment and inflation, or what is the influence of cost of living? So these kind of questions can be generated using iSeek. And then it will be written back to the user. Let's talk about functional grounding. So functional grounding help us to factually verify, reducing hallucination and external knowledge integration, and also error categorization. So for attribution-based system, we have like 3 types of labels, like attributable, extrapolatory, and then contradictory. So in attributable, basically the system will identify that can we find the correct resource of this sentence or not, or the information have like multiple sources of this information, and this information doesn't match with the other source, and sorry, that will be contradictory. And then exploratory, can we identify more than one information? Now, how we can do that is that reinforcement learning for grounding. So we can actually use a response query and then use a reward model that scores our query context and the response. And then the model can be trained on the data set specifying preferences between response pairs. We can use this by using like a KL divergence or an initial model. So this is another example of using a reinforcement based grounding. So in reinforcement based grounding, basically, this is an example of code generating language model, which is where it is acting as an actor network and introducing a critique network that is trained to predict the functional correctness of generated programs. And then it is providing back the feedback signals to the actor. This is a specification where it is asking like if a string is a palindrome and can you provide the solution program. So if you remember if you go back to 2022 when LLMs like ChatGPT came, it will provide like a very naive example, and that to be not true. It was always giving up errors. So now this reinforcement based grounding, which OpenAI actually enforced, and it was able to perform well. And the current example you can see is that O1 reasoning coding example, coding model, where you can find this answer correctly, that if it is asking a palindrome, it was able to provide a correct palindrome answer. We have our one of the paper, which is for the data set, interactive and reinforcement based grounding at AAAI. We will be presenting it on 28th Feb. So you can know more about our data set, how to do interactive and reinforcement based grounding. And it is about code obfuscation. And you will find more details in our poster. Grounding verification. So till now we talked about how to do grounding generation, but also there is an important part of grounding verification where we need to identify that generated answer or the claims are true or not. So why this is important? This is important for like healthcare, if a query is complex, and if we want to verify like the example which we saw earlier about the blood pressure one, and also the law example. So this is on the previous slide, output of the previous slide, which I explained the information, and we are now doing this symbolic and functional grounding together because we want to see that if given a input where user wants to identify that a given answer by the LLM models, what is this about? So identifying like if it is a depression or not a depression. So earlier we saw that if we are doing just with llama, and that llama was producing a very generic answer. But if we combine with a domain knowledge like PHQ-9. So we learned about PHQ-9 in one of our earlier talks. So PHQ-9 ontology will infused with the llama, and then it was able to provide the correct output. So the output look like this, that the speaker describes carrying a heavy burden, feeling that family is feeling irritably, emotionally disturbed, and the speaker's actions may cause more harm. So this is like symbolic and functional grounding together, where it is adapting to the domain knowledge. And this is our work is published in JBHI IEEE. So you can check out our paper also for more details. But how we do this symbolic and functional grounding together. So we start with a depression specific phrase embedding. We combine it with the for the knowledge infusion. In knowledge infusion, we combine it with the ontology and embeddings together. Now, for each of the 9 questions, we have separate attention layers and embeddings. So we concatenate those attention layers and embeddings together to predict a depression classifier. And why we are using 9 layers? Because there were 9 questions in initial phase, and those 9 questions are serving as the different layers. So this was actually able to generate and retrieves the clinical information from this ontology which we are providing. And this can be used as like we are actually citing to the PHQ-9 ontology for our work. Let's see how does it performed in within one or two examples. So this is the original text about a depression, and here user is explaining like what that user is feeling from the past 6 months. Now, if we use a normal like self-attention layer classifier or a large language model, it was not able to identify any of the attention. It was basically not able to focus on any words that can identify the mental health terms. Now, these are the questions which were in the PHQ-9, like how often have you been bothered by little interest or pleasure in doing things? There was no highlights when we were using self-attention. Another question was how often you are bothered by feeling down, depressed, and hopeless. So it was able to identify few words like depression, stop working, because these are more of the general purpose LLMs where it can find these kind of words and it can give some attention to these words. Then in question 9 also it was able to identify which can be found in like the general purpose LLMs. But the problem was why it is not able to identify all the 9 questions and what kind of terms you have to identify when if we are using clinical terms. So we checked our results. So this is self-attention and with the PHQ-9 questions that it was not able to identify properly. It was reaching like a cumulative self-attention of 1.4. But when we did with our cross-attention layer, like I explained it earlier, with infusion of PHQ-9 ontology, it was able to identify actual questions like PHQ-2 or PHQ-4, PHQ-7 and PHQ-9, that these are the words which are present in the given text. And these words can actually help a mental health expert to identify that what a person is feeling. It will be very easier for them to work with those kind of clinical terms rather than working with the whole text, and which will be like time consuming and cumbersome for them to identify all these words. So this is one of the Google Cloud grounding API where you can actually see if you can do the grounding scores that can support score like contradiction score, citations, anti-citation. All you can do, just go on this link to try out how you can check your grounding in the given post or in the, so this is like kind of an example which Google API is currently running, and you can find score between 0 and 1 for identifying the grounding. So I will leave with some open questions here that still in grounding, we cannot we are very uncertain of finding and unverified information for which there are no claims. And how should LLMs handle conflicting information? There is still that question remained. Also, can LLMs to cross-references their outputs or not? So these kind of questions are still remain.
Oh, we saw it. It wasn't plugged in. No.
So before I hand off, any questions? Okay, I'll hand off to Ali for the next talk.
Hello, everyone. Thank you for your patience. Today, I will talk about explainability of part of this discussion. I will go inside the models and check the explainability on large language models. Our key focus would be on wellness dimension, but I will try to skip these parts as Dr. Gore discussed it on the very first slides. We will talk about explainability. We will check the impact of external knowledge into large language models and large language models. So we have different kinds of different wellness dimensions, like physical, intellectual, vocational, social, spiritual, and emotional. So consider this example. We have a textual post as the input. And as you can see, those blue parts are the most important parts of the sentence that given to an expert, they can provide you the label and also the explanation for that label. So we want to check if the model also focus on the same thing that experts focus on. We will try fine-tuning LLMs, prompting LLMs, and we try these two wellness dimensions. So what we expecting is a label and explanation. So this is the entire the framework that, as an example, that we consider. So for the external knowledge, consider the first row. This is for ESNLI dataset, which is a entailment dataset, and it's general dataset. We have a pair of premise and hypothesis, and also a label, which is going to provide the relationship between these two P and premise and hypothesis. So the output would be a prediction, which can be entailment, neutral, and contradiction, plus an explanation, which is going to represent the reason behind the label. So in the part A, we just use the input sample, that premise and hypothesis, to the Llama model, and it ends up with entailment and that explanation, which is not correct. If you read the explanation, it says the hypothesis is entailed by the premise because the description of the doctor and her assistant in the premise doesn't provide any information that would contradict the hypothesis. If we consider this explanation, we can end up with it's neutral, in fact, because it doesn't represent anything from the from the premise and hypothesis. So, but the model end up with misclassification. The reason might be it knows the definitions for those labels, because at least for this explanation, it provides the definition for the neutral label, but it didn't end up with correct classification. So in the second scenario, we try to integrate label definitions, in this case, entailment, contradiction, and neutral, and we can see it end up with correct classification and also correct explanation. So this is the main point of like our idea to start work on. But still we have some like space to how can we sure that the classification comes from the definition that we provided, not the internal knowledge of the model. So to check this, we assume if the model relies on its own knowledge, right, and it end up with like a performance, like MCC, and then we provide incorrect definition, like permutation of these definition, like instead of providing correct definition for entailment, we use contradiction label. We use contradiction explanation. So if the model relies on its own knowledge, we expect it end up with like similar performance because it's on own knowledge. It doesn't, it ignores the provided or the integrated knowledge that we provided. And in another scenario, we try to change the definition a little bit or even make it incorrect. So out of these scenarios, we end up with these findings that when we have, first of all, we have MCC with definition, and the second one is we have MCC without definition. So for ESNLI dataset, which is a general dataset, and we know that it knows the definition for each labels, we can see when we provide the definition, it ends up with lower MCC score, which means the model relies on its own knowledge. But for hate-explained dataset and well-explained dataset, which are a specific domain dataset, we can see with definition, I mean, when we provide definition into the input, it ends up with higher MCC regarding to when we don't have definition. So in this framework, we try to check the robustness and explainability of language models. Just in what we can see on the right side, we can see that we have a textual post, we have output, which is those labels for wellness dimension. And for evaluation, we have the post and we ask the model to end up with a label and explanation. So for robustness, we use sigmoid cross entropy and gambler loss. The reason we try gambler loss is when we use gambler loss, we expect it end up with higher performance, because with gambler loss, the model avoid to end up with any prediction when it's not confident enough. So we expected it end up with better results with gambler loss. For explainability assessment, we try SVD ranking and attention overlap score. So for SVD ranking, we just focus on the attention metrics and we try SVD ranks. And lower ranks suggest that the model focuses on fewer parts of the sentence, and which means it's like whatever humans are doing. For attention overlap score, simply we just try the number of common words between grounded and generated explanation divided by the total number of grounded truth words. So using SVD for multi-WD and well-explained data set, we end up with these results for BERT, Roberta, ExcelNet, Ernie, clinical BERT, psych BERT, and mental BERT. Out of these, we can see the Roberta for well-explained end up with better results regarding to gambler loss. And for attention score, attention overlap score, we can see that gambler loss end up with better result as we expected for all of these models. So this is an example of SCC versus gambler loss attention. The parts of the sentence that are red or in different colors, those means that the model focus on these parts of the sentence, and in the gambler loss, we can see it focus on more parts of the sentence regarding to the SCE loss. So for future directions, one could be focusing on what is the reason behind the disparity between the accuracy and attention for SC and gambler loss. Second, improving attention alignment with ground truth. Exploring different prompting and RAG strategies to check more on the explainability parts. And finally, developing a suitable data set for mental health applications. So this is the main work that is presented before in EMNLP as in the black box workshop. Reference, and if you have any question. Okay, so regarding to the next presentation, which is OpenCha, it's for like Iman Azimi, which is I think available online, but I will present it on I will present on behalf of him, but he's available if you have any question. So OpenCha is a framework to like assist patients and healthcare providers like clinical decision support, patient monitoring and follow-up, chronic health management, patient self-awareness. So there are some reasons why these chatbots are not widely used, like trustworthiness, personalization, data analysis, access to up-to-date information, and explainability. So OpenCha is, in fact, conversational health agents, which is a framework to integrate health data, knowledge, and analytic tools into healthcare chatbots. As you can see here, we have users, we have some different components in these chatbots. Like there is one for personalized conversation, which could consider multimodal data like text, image. It it could cover multi-language, and also it should be supportive to provide a supportive response to the users. So health agent is responsible for understanding the query, think and plan for it based on its knowledge and whatever it collect from other resources. It access the data, it end up with answer, and finally it try to provide a understandable human-like answer. So this is how this framework works. As you can see, first we have an interface which includes which can be mobile application, web application, desktop application. It's something that it's the bridge between the users and agents, and it receives the queries from the users and metadata, which metadata could be text, images, or medical test or something. All of these could be considered as metadata. And after receiving these data, what orchestrator is doing is it receive the input data and then aggregate, transform all of those into a structured data, analyze these data using the toolbox that it has access to, and end up with a plan and execute those plans. So it interacts with external sources to acquire the required information. So it could be something like another model which is trained on a specific data or a specific task. And so consider this, when we use like GPT or any other LLM, we provide everything in the prompt and ask to provide the answer, right? But what in this component is doing is when it receives the input, it analyzes those inputs. And if it needs to, for example, use another model, which is like more specific to a subtask, it asks that model to provide the more appropriate data regarding to the task, and then use those to end up with its final answer. So the external sources could be AI and analysis models. It can be a knowledge base. It can be healthcare data source. All of these can be like external sources that the agent use to end up with the final source, final response. So this is a demo for the work. Let me try if it.
In this video, we demonstrate an example of personalized food recommendations on OpenCHA. We first select the tasks that OpenCHA can perform to generate the response. We select the task to interact with users' food data and health outcomes collected from external wearable devices, and one task utilizing causal inference algorithms to estimate nutrition effects. Then we take two tasks retrieving food nutrition content relevant to the user's query and requesting additional information from the user. Let's start by asking the agent to show my personal nutrition effects on In this video, we demonstrate an example of personalized food recommendations on OpenCHA. We first select the tasks that OpenCHA can perform to generate the response. We select the task to interact with users' food data and health outcomes collected from external wearable devices, and one task utilizing causal inference algorithms to estimate nutrition effects. Then we take two tasks retrieving food nutrition content relevant to the user's query and requesting additional information from the user. Let's start by asking the agent to show my personal nutrition effects on a specific health outcome, such as deep sleep. To do this, OpenCHA will collect data from a food log and deep sleep information tracked by a wearable device, subsequently estimating the causal effects of nutrition on deep sleep. The response will reveal the nutrition effects on deep sleep, with values indicating the estimated average treatment effects of the nutrients per unit. We can also ask for food recommendations by querying the foods to improve certain health outcomes. For example, we say could you recommend me a food to improve my deep sleep duration? This will trigger the agent to execute the retrieve food task to obtain the relevant foods and their nutrition contents and personal nutrition effects. The response demonstrates the food suggestions to improve the deep sleep and the explanation based on the estimated personal nutrition effects. The recommendations are explainable. By querying with "Please explain your recommendations," OpenCHA will display the rationale behind the food choices, focusing on their nutritional impact. But what if you're missing an ingredient or food? No worries. OpenCHA's interactivity comes into play. Remember that this isn't just a static food list. It's a conversation with your dietary needs. Ask a follow-up question like, "I don't have the recommended foods. What are my alternatives?" And OpenCHA adapts, offering alternative suggestions. By calling the tasks, OpenCHA not only delivers nutrition-oriented food recommendations, but also enhances the user experience with personalization, explainability, and interactivity. This ensures a more user-friendly approach, tailored to individual needs and preferences, enabling users to make informed dietary choices and adapt suggestions to fit their unique health goals and lifestyle.
Well, problems made history today. And so today became a day that will live in infamy in presidential history, because today.
Sorry for that. I cannot count anymore. Not really. Oops. Wait, let's see.
So here's a slide.
Okay, sorry for the interruption. So we have some record reports samples here, which shows the tasks that are involved in For example, in the first one, we can see that get data, statistical analysis, internet search, and extract text. For the second one, we have, again, get data, statistical analysis, SERP API, and extract text. And here, which is going to like estimate the level, the stress. It's first it get the data, then it has HRV extraction, which is a stand for heart rate variability. And so in this case, consider we have those data which are kind of signals, right? So instead of providing these signals directly to the LLM, it uses another model which is trained on these signals. And then when it get the response from that sub-model, and then use those information or knowledge to end up with its final answer. So there are thank you. These are some use cases that this chatbot is used in. So the future direction could be working on safety of the responses, connecting more external sources like data sets and knowledge graphs, and finally, like chronic health management. Thank you very much. If you have any question. Thank you. If someone has any question, those who are online. Thank you, everyone. If you want to have these slides, you can check that web page. And for any other question, you can contact these emails. Thank you. Sorry. Sure. Yeah, you can go to the slides section here to get the slides.
So we will also be uploading data set and code that we sort of use and discuss with the tutorial today on the website. And if you have any questions, you can email me, which is manas@unbstudy. I'm getting from the slide deck, so. We'll end the session. Thank you all for your attention.